This is a finite state machine diagram describing the RAFT consensus algorithm. And this chain is running by interpreting that diagram. So we obtained a blockchain where the consensus algorithm is implemented by a WebAssembly smart contract that can be upgraded or fully changed through a governance process while the blockchain is running. You cannot have decentralized blockchains without this type of flexibility that makes development governable. By using smart contracts for the core protocol, you can spawn other blockchains with a different consensus protocol or data encoding from a main guardian chain. You can have flexible scaling by sidechains or parallel chains or by a rollup mechanism. So let's dive in the RAFT diagram. First, RAFT works by choosing one leader at any point in time. In the classical version, any node can become a leader, and only the leader can collect, propose, disseminate, and commit data changes. So in our case, the leader will be the one proposing, disseminating, and committing blocks. The classical RAFT is targeted at databases, not blockchains, but even in this form, you get a federated blockchain database where you can prove data authenticity and track data changes in time. We can also update the RAFT protocol to include block verification from all nodes and slashing of the leader or follower nodes if they misbehave. You can separate the state machines needed to implement RAFT and have a different state machine for leader election and another one for log replication and another one for membership changes. But for this version, I created one state machine for all three. After the state machine is initialized and started, nodes can be either a follower, a candidate, or a leader. All nodes start as followers, and they start a random time interval that has a minimum and a maximum value. When the time interval is ended, and this time interval is called election timeout, they propose themselves as candidates and they request votes from other nodes. Now, if they get enough votes, they become a leader. If the leader stops, then the other nodes start the election process again. In the follower state, nodes can just receive messages, either vote requests from other candidates or heartbeats. And these are messages from the leader. These heartbeat messages are a way for the leader to signal liveness and also for the transport of new data entries. And in our case, these are blocks that are produced. If the follower receives blocks, it verifies them and commits them. And we have implemented this system on top of the Cosmos SDK. So when processing append entries, when processing the blocks, a follower uses the process proposal, finalize proposal, and commit methods from the Cosmos SDK app. So the blocks are validated and then finalized and committed one by one. The follower can also receive new transactions from users, but it does not process them itself. Instead, it forwards these transactions to the leader. In candidate state, if the node does not receive enough votes to become a leader, then the candidate reverts to the follower state again. In the leader state, the leader has another type of timed action, the heartbeat mentioned earlier. So the smart contract starts a timed action that will execute an external state transition back to the leader state. And when the state is re-entered, it will execute all these re-entry actions. So each time the leader will disseminate the new blocks that were created It will commit the blocks that have been disseminated to a majority of the nodes, and it will propose the next block. Other events, like receiving a new transaction from a user or forwarded by other nodes, trigger an internal transition. So this internal transition does not re-execute the entry actions of our leader active state. And there is another event here, node update, and this is related to membership changes, but we will not enter into details now. Now, this diagram is built with stately and can be reduced to a JSON configuration. So let's look at this JSON configuration here. This configuration is interpreted by a state machine interpreter contract that I wrote in AssemblyScript. This contract receives a state machine configuration and optionally a contract address with functions customized for that state machine, and treats the state machine as a standalone contract. So we have integrated this system into the Cosmos SDK and fully replaced Tendermint or the Comet BFT Golang module. And I have rewired the blockchain to send transactions and queries to this RAFT smart contract when transactions are broadcasted or when blocks and transaction information is requested. And this contract uses special consensus host imports that are available only for core contracts with a consensus role. And these are the methods compatible with the Cosmos SDK protocol for checking transaction validity before being included in a block, for preparing the block proposal, processing the block proposal, finalizing the block, committing it, and rolling back the Cosmos app to a certain height if needed. So let's see it in action. I have two nodes here, and when we first start them, they are in the follower state. And the first one to finish the election timeout will try to become a leader. And we already see that the first node has become a leader, and if we look at the logs here, it has sent vote requests, and the other node has voted for the candidate with ID 0, which is the first node, and the leader has immediately started to produce block proposals and disseminate and finalize blocks and so on. And the follower has started receiving these blocks. So all logs starting with RAFT are coming from the RAFT state machine, finite state machine contract, and we can see here RAFT calling commit, the block being finalized, and then proposing a new block, batching the transaction that it has, starting the block proposal, calling the prepare proposal function, and then the process proposal, and then saving that block to storage, and then starting another timed execution for the next heartbeat and ending the current execution. And this is where the next execution starts again. So after the heartbeat timeout delay, this node is in the leader active state, and after executing that delayed action, it applies a transition to the same state. It executes what guard we have there, which in this case there is no guard, and it executes the three actions that it finds as entry actions. It disseminates to the other nodes what blocks it has committed, and it does this by sending a gRPC request to each node. The next action is committing the already disseminated blocks that have been received by a majority of nodes, and then it starts the block finalization It calls finalize block from the Cosmos app, and this request is executed. Then we are updating the current state, which contains the latest app hash and block ID and so on. And the follower continuously starts a new election in case the leader doesn't send heartbeats anymore. So it starts a new election. This election is stopped whenever it's reset whenever the leader sends a heartbeat, and when this node receives heartbeats from the leader, then it processes them. It does process append entries, and it takes the new entries. We've received 1, which is 1 block. We then run the process proposal and save the entry and start the block finalization. And again, we call the finalize block from the Cosmos app and commit the state. We update our consensus state and parameters, and we continue the process. Now, the trickiest part from this is the timed actions, like the heartbeat and the election timeout. And these timed actions are triggered by the smart contract, but they are executed by the Golang code wrapping the WebAssembly contracts by spawning Go routines. So while the blockchain is running, we can also send a transaction. Let's copy this transaction hash. And we can look at our block explorer at block 272. And we have here our transaction hash. Let's open the transaction in another window. So you can see it is a message instantiate contract transaction with all the events and so on. All the blocks and transactions are actually read from the state of our consensus smart contract, from the RAFT smart contract. So we can have actually blockchain introspection that can be read from any contract. So the blockchain has been rewired to read this transaction and block data from our consensus contract. In the next videos, you may see improved versions of RAFT for blockchains, Tendermint BFT, and other blockchain consensus algorithms implemented in the same way.